spite of the weather, thank you for making an effort and being here. This is a particularly special one of our endowed lectures because of a couple of things that I will share with you soon. So first let me take a few minutes and just introduce what this lecture series is all about. So a number of years ago, before I became department chair, my predecessor had an opportunity to communicate with Dr. Don Donaldson, and he, through a very generous gift, decided that he would like to honor the memory of his late wife, Lois McGlothlin Donaldson, in the form of sponsoring an annual lecture, which is now what we are attending. We host this every spring, and we have the opportunity and the privilege, through this generous gift, to invite highly distinguished, celebrated scientists in their field to come and share their discoveries, and we are able to open this to the public, so we are extremely thankful to Dr. Donaldson for this generous gift. His late wife was a student here at the U of M, and she majored in art history. Because of her love and passion and interest in astronomy, this lecture series became a possibility. And we have enjoyed the speakers that we have had these 7 years. Tonight's lecture is particularly special because we have been celebrating this event. Now it's the second day, and tomorrow we will continue with the celebration. The event that you are attending is day 2 of celebrating the installation of a scaled solar system model here on our campus. This is a one-of-a-kind, certainly in the region, and definitely in Memphis, and it has been a project that has been in the works for a number of years. If you have not already had the opportunity to walk the solar system, please take advantage of it on a day with slightly better weather. And we have all the information on our department website for you to go and look. There is a storyboard, and our distinguished speaker tonight has kindly narrated each of these storyboards, and all of that information is uploaded. We will share that information with anyone who is interested in knowing where to find them. They are also downloadable. This project started at the beginning of COVID. From the moment that Joanne approached me about this subject, I was very excited, but we knew it's going to be a long road, from the crowdfunding that we had to do, to the ordering and the shipping, to the logistics of getting it to campus, to get the installation done, to the point where now we can actually see the result of it. It has been a long, arduous road, and we thank all of our donors for their generous contributions, everybody at the U of M who contributed to this effort, and all of those who attended yesterday's celebration, today's celebration, this evening, and tomorrow. We have an opportunity for school teachers and others in the community to come and have some time with our distinguished speaker. I would like to add a personal note of gratitude to my colleague Joanne Rose for her tenacious and absolute dedication to this project and to this lecture series that we hold. She does a wonderful job. Please give her a round of applause. So I'm going to leave it to Joanne to introduce our distinguished speaker, who is an inventor, an author, a scholar, an educator, and everything else that we can celebrate.
Thank you. Can you hear me? Okay. That was very very much appreciated, and I'm so glad to see you all here. I know that there are a lot of events in one 3-day period, but hopefully that just helps more people have access to getting to hear Dr. Bennett speak. I want to tell you that I first saw the Voyage solar system at the Smithsonian about 20 years ago, and I was so impressed. It gave me such a different view of our place. And it made, I was already, I don't know if you can see, but I'm wearing the Earthrise picture. This is what I teach in because it's really important to me that we take care of the Earth. And the Voyage solar system, to me, does the same thing as this Earthrise picture because it shows how lucky we are, how special it is to be here on Earth, because there is nothing else in our solar system like Earth. And global warming, I've told my classes for several years that it is my biggest concern. And that's hard to say because I have a lot of concerns. I have a whole lot of concerns, but global warming has definitely been up at the top. And I hope that we can, well, get some hope from Dr. Bennett tonight of what we can do, what we might be able to do to turn things around. And he's my astronomy book author. So I've taught from his books for more than a decade, and I have thoroughly enjoyed that. And he was also involved with, the solar system, and I didn't even realize that he had done that part until I was trying to get the one here. I'm so glad we got it, and I hope that you will all get to see it another time, because I know it'll be dark when we get done. Anyway, Dr. Bennett is just an incredible educator. He's got so much enthusiasm for teaching, and I am so thrilled to have him here. So I'm going to welcome him. Please help me welcome him.
Thank you very much. Thanks for coming out tonight. I really appreciate having you all here. And so I'll just get right into what we're going to do. I'm going to move pretty fast tonight so you can see the title of my talk, Pathway to a Post-Global Warming Future. What is a post-global warming future? That's a future where someday today's college students will be telling their kids and grandkids about this problem that we used to have that was very serious, but that is now in the history books. That's the idea that we're shooting for here. I'm going to give you a brief overview of the science, consequences, and solutions of global warming. I want to give you just a little background on how I got to this point. Well, first, I've been teaching about this topic for more than 40 years, believe it or not. When I first started teaching astronomy in 1982, I was teaching global warming, and you'll see the context in just a few moments. And has an interesting connection to the theory of relativity for me personally, which is that back in 2015, we had the 100th anniversary of Einstein's publication of his general theory of relativity, and I had written a book on Einstein's theories, and so I decided, well, I'll just go give tours, lectures, wherever people want me to. And I ended up in about 25 cities talking like 10,000 people about relativity. And it was really fun, and then the 100th anniversary was over. I was like, well, what do I do now? And so I thought, well, maybe I'll do it talks on something else. And I thought, well, global warming, I've been teaching about it for a long time, it's really important, and so I started doing these talks on global warming. And my title at the time was Global Warming Demystified, because I felt the most important thing to do was sort of to get people over the understanding of exactly where this idea comes from and why we as scientists think it's a very serious issue. And then, things kind of shut down because of, COVID, for a little while. And it was time to start back up. And it was really interesting to start talking to people again and realizing that there's been a big change in just these last 7 or 8 years in the way people think about this topic. I used to run into a lot of people who weren't sure it was real. That doesn't happen much anymore. And I think probably because we've seen so many of the consequences that we'll talk about. And instead, what I'm finding, particularly among younger people, is what you might call despair about this topic, that the world is really in a bad place and doesn't seem like there's anything we can do about it. And that's why I switched to this focus, and hopefully I'll convince you there are things we can do about it. Incidentally, I'll try to go through a lot of the basic ideas tonight, but I have a book that does in Q&A form all of it called Global Warming Primer, and it is posted for free online at globalwarmingprimer.com, so you can go there to look. There's also, you can of course get a book version of it, but it is all there online. And then my regular general website is bigkidscience.com. Anyway, the talk title starts with a post-global warming future. So what is the future? And I just put the question up there because something probably pops into your mind when you see that question. And we won't go around the room to see what popped into your mind, but it probably depends on who you are and where you are in your life. For example, if you're a college student right now, what is the future? You're probably thinking about your graduation. When's that going to be? And what will your first job be? And so on. If you're a media person, well, if you look at what happens with the media, you find that most media reporting on this topic is, here's what's going to happen by 2030, or maybe here's what's going to happen by 2050. But it's very rare to see any articles in the media that take you much beyond about 2050. And yet, when you think about it, you'll realize that pretty much everyone who's in college today or younger is very likely to still be alive in the year 2100 and beyond. And just in case you're wondering why I say that, life expectancy in the last 100 years rose by about 30 years. So even if we do less than that over the coming rest of this century, by the end of this century, we can figure life expectancy will probably be close to 100 years, which means that anybody born since the year 2000 has probably at least a 50-50 or better chance of still being alive in the year 2100. And so that's the future that we need to be talking about, and yet we never do. We're always focused on a much shorter term. And so if you're a younger person who's going to be alive in the year 2100, or if you have kids or grandkids who might be in that situation, you might start thinking, even before we go through the rest of the talk, what are the stories that you're going to be able to tell about the impacts of global warming when we reach your 100th birthday? If you follow what's going on in the media, you'll tend to think that those choices, that the stories you're going to be telling, will be either that the future has become bleak or bleaker. But even though that's what we hear most of the time, it doesn't have to be that way. And the reason it doesn't have to be that way is because if we understand the issue and what's causing it, then with understanding, we can come up with solutions. So what we're going to do tonight is we're going to start with the understanding. So I told you science, consequences, solutions. So I'm going to start with the basic science of global warming. Just as a quick note, also known as climate change. Very subtle difference maybe between the two terms. We can use them interchangeably. But I think of global warming as this general average increase in Earth's temperature, whereas climate change is all the many different changes that are occurring because of that general warming trend. Now, I told you I started teaching about this in my astronomy classes because it turns out that global warming is really an astronomical topic. And I think actually the best way to get a grip on the basic science of global warming is to start out with astronomy. And so what you have here is what I'm going to call a tale of two planets. And you see Earth and Venus on the screen, and they are shown here to scale. And what you notice right off the bat is they're basically both the same size. Out in the scale model solar system, you'll see that too. Earth and Venus are the same size. Not only are they the same size, but we know from spacecraft data and other measurements that they have the same average density. They most likely have the same internal type of layering, same composition. In fact, in most ways, these two planets are probably as close as you can get to being identical twin planets. As is possible anywhere, except for one thing. And the one big difference between them is their average surface temperatures. On Earth, very pleasant here on average. On Venus, not so much, hot enough to melt lead on the surface. And so if you're thinking about this from a scientific viewpoint, think like a scientist is what I want you to do, you might say, well gosh, why would two planets that are so similar in almost every other way have this one big difference between them? And if you know the way science works, you might come up with a hypothesis to explain it and then test it out. What hypothesis might you come up with? Well, if you're like most people, your first hypothesis is going to be it's because Venus is closer to the sun. But it turns out that doesn't work when you test it out. And here, this is a picture of the model solar system in DC. I could have stuck one in of yours here now, because it's the same scale. But there's the sun at the 1/10 of actual size, and Venus and the Earth. And the way I like to think about it is imagine that we had a big bonfire here at the sun, and then you walk over and stand at Venus and stand on Earth. And you can do this now outside here, and just sort of imagine in your head, what would the temperature difference feel like? And you'll see, of course, yes, you would expect it to be warmer here at Venus, but you'll see the difference just isn't that much. And in fact, if you calculate it out, you'll get a more precise result. But yes, the distance cannot explain that temperature difference. In fact, since I know we have a pretty sophisticated audience in here, we'll go one step further and say there's another thing that you might notice down here, which is that Earth has a few clouds and Venus is completely covered in clouds, and you know that clouds reflect sunlight. And as a result of that, it turns out that even though Venus is closer to the sun, it's got so much cloud cover reflecting sunlight that actually less sunlight reaches its surface than Earth's. And therefore, because of that, Venus should actually be colder than Earth because it's getting less sunlight on the ground. But it's not. It's really, really hot. So why? Well, we could keep hypothesizing, but I'll just tell you the answer. And the answer is the greenhouse effect. You're probably familiar with the greenhouse effect. Sunlight comes in and warms a planet's surface, and the planet has to return that energy back to space, but it doesn't do it in the same form of visible light. Well, there is some visible light reflected. That's why we can see planets in the night sky. But the sunlight that's absorbed, that gets returned back to space in the form of infrared light. And infrared light, these blue dots represent what we call greenhouse gases. On Earth, the three most important greenhouse gases are water vapor, carbon dioxide, and methane. And what happens is when infrared light hits one of these molecules, it gets absorbed and re-emitted, but in some random direction. And so the net result of all this is that the greenhouse effect traps energy down near the surface. So adds energy to the surface, oceans, and lower atmosphere, making a planet warmer than it would be if it didn't have these gases absorbing that infrared light. And you can see the basic idea. If you put more of these blue dots on here, then it's going to be even harder for that infrared radiation to get out, so you're going to trap even more energy. And the way I like to think about how this works is just to think about a blanket as an analogy. If you go outside on a cold night and you wrap yourself in a blanket, you warm up. But if you think about it, you might wonder why. The blanket's not giving off any heat, so why are you warming up? And the answer is because the blanket is trapping your own body heat and preventing it from escaping so quickly. It exactly like the greenhouse effect. So the greenhouse effect is like a blanket for a planet, and more greenhouse gases means piling more blankets on top of it. And so that explains our difference between the two planets, and I'll come back to it in a little bit. But before I do, I told you that I wanted you to think like a scientist, and if you're thinking like a scientist, you would probably say, well, gosh, that was a nice story you told us about the greenhouse effect, but why should I believe you? And why should you believe me? Because we have evidence to know that the greenhouse effect really works the way I just showed you. And we actually have two basic lines of evidence. The first is you can actually measure this effect in the laboratory. Basically, this is showing you an apparatus from 1859 that was used to make the first greenhouse effect measurements. Although he wasn't the first person, John Tyndall, to make any kind of related measurements, there were some measurements made earlier in 1856 by a woman named Eunice Newton Foote, and for some unknown reason, people forgot about her contributions for about 150 years until they were rediscovered. And you can read about why they forgot about her contributions. And probably won't be too surprised by some of the answers you run into. But anyway, John Tyndall's apparatus, basically you put gases in a tube, shine light of different wavelengths at it, and you measure. And when you have enough measurements of the greenhouse effect, then you can use that to calculate what's going to happen if I have a certain amount of greenhouse gases in the atmosphere. And so from these measurements, we understand the greenhouse effect really precisely, and these measurements have gotten better and better and better, and they've been done for a century and a half already. In fact, already by 1896, the measurements were so well known that the famous chemist Arrhenius was able to actually calculate what would happen if we doubled the amount of carbon dioxide in Earth's atmosphere. And remarkably, the answer he came up with is virtually identical to what the very best climate models now tell you. So it wasn't complicated. Well, it did take him 2 years of calculations to get the answer, but that's because it was pencil and paper. But we have those predictions, and then we can test those predictions with actual planets. We compare the predicted and actual temperatures of planets. And what we find is that if you predict the temperature of a planet without the greenhouse effect, or with any other guess you might have, you get the wrong answer. But if you predict it with the greenhouse effect, you get it with the right answer. So we have real world evidence demonstrating that our laboratory understanding of the greenhouse effect is correct. And one of the really interesting things about it, this is the actual equation without the greenhouse effect for a planet's temperature based on its distance from the sun and its reflectivity. And you can see that for Earth, that's a negative sign there. For Earth, without the greenhouse effect, the temperature would be negative 16 Celsius, so well below freezing. In other words, without the greenhouse effect, this planet would be frozen over. And so that brings us to the conclusion of our tale of two planets. Why is Earth nice instead of frozen? It's because we have enough carbon dioxide to make our planet livable. And so in that sense, you would say the greenhouse effect is a very good thing for life, because we wouldn't be here without it. But if you go to Venus, why is Venus so hot? It's because it has 200,000 times as much carbon dioxide in its atmosphere as Earth does, so 200,000 times as many blue dots. And that's what causes it to be so hot. And that right there is really all you need to have absolute proof that while the greenhouse effect is a very good thing for life, it's possible to have too much of a good thing. And now that we know it's possible to have too much of a good thing, you might say, well, what's the relevance of that to us? Well, the relevance of that to us is that the concentration of that good thing is going up because of us. So this is the famous data from the Mauna Loa Observatory, sometimes called the Keeling curve, after Charles David Keeling, who first made these measurements in the late 1950s. And what it's showing you is the amount of carbon dioxide in Earth's atmosphere measured in parts per million. So basically, like if it says 320, that means that out of every 1 million molecules of air, 320 of them are carbon dioxide. And you can see that back in the late 1950s, it was about 315, and today we're now up over 420. So it's a substantial increase. Why is it going up? It's going up primarily because of the burning of fossil fuels. I'm not going to go through all the details of how we know that right now, but the smoking gun evidence, for those of you who will understand the science part I'm about to say, is the carbon isotope ratio of biology and fossils is different from the carbon isotope ratio of volcanoes and inorganic sources. And as this carbon dioxide concentration has been going up, the carbon isotope ratio has been changing in the exact way that could only be happening if this was coming from the burning of fossil fuels. So there's no doubt at all that it's the burning of fossil fuels that's the main thing behind this. And so really the only big question that you might still have about what's behind this basically is, even though we know this is due to us, are there ever any natural changes that might be similar? And to answer that, you need records of the carbon dioxide concentration going back much further. You might think, well, how are we going to do that? Nobody was measuring it. But of course, there's many ways scientifically to figure out what the carbon dioxide concentration was further in the past. And the most reliable records come from these ice cores where people drill down deep into the ice. I think it's on the par with the moon landing, the biggest deep ice core that's ever been drilled. Back in 2007-8, they drilled down 2 miles into the Antarctic ice and brought up 2 miles long of ice core depth. Well, how does that help people? What is that ice? Well, that ice is snow that fell and piled up year after year after year. And because of seasonal changes in the size of ice crystals and so on, you can actually see the layers in these ice cores. It's like looking at tree rings, basically. And so you can count back and see how many years in the past you're looking. And it turns out in that 2-mile-long ice core, if you count down, you find that at the bottom, you were pulling up ice that represents snow that fell 800,000 years ago. And as a result of that, there's air bubbles trapped in the ice. You can look at those air bubbles, measure the carbon dioxide concentration in them. And as a result of that, we have an 800,000-year record of the carbon dioxide concentration on Earth. So here's today, 0, going back 800,000 years. And what you'll notice is that sure enough, the carbon dioxide concentration has varied a lot. This is obviously natural variation because we weren't burning any fossil fuels back then. We didn't start till around the year 1750 when the concentration was about 280 parts per million. But what you'll notice is that throughout that whole period of time, it stayed in this relatively narrow range, 180 to 280, 90 parts per million, which means our level today at 420 is about 50% higher than it was at any time in the last 800,000 years. And if you extrapolate this curve upward, if you say if we keep doing what we're doing today, we will reach double that pre-industrial concentration, so 560 parts per million, in only about 50 years. And if we kept going beyond that, we'd be getting close to 1,000 parts per million, triple the pre-industrial concentration by the middle of the next century, and so on. And so now we can summarize the science of global warming that I've explained to you in 3 very simple steps. So I like to call it global warming 1, 2, 3, so that if you're trying to remember how does this science work, all you have to do is remember these 3 basic things. And the first is that it's a fact that carbon dioxide makes Earth warmer than it would be otherwise. We know it's a fact from those measurements in the planetary data I showed you. There's no dispute about this at all. Number 2, it's a fact that the use of fossil fuels is adding carbon dioxide to the atmosphere. Again, no doubt about it at all, because we have those direct measurements that we talked about. And if you put number 1 and number 2 together, more carbon dioxide means higher temperatures, and we're putting in more carbon dioxide, number 3 is pretty obvious. It's going to get warmer. No way around this basic conclusion. It's got to get warmer as a result of what we are doing to this planet. And the data show, sure enough, it is getting warmer. This is the temperature record going back to 1880, and very, very clear that it's getting warmer. And in fact, notice that the most recent 9 years here are all hotter than anything else in that entire temperature record. So we've had just right now the 9 hottest years in the past 9 years. And this trend will almost certainly continue in exactly the same way going forward. Now, you might want to get some context on that. what does this temperature change look like compared to past temperatures? And so we can use those same ice cores that I showed you before to figure out what the temperature was in the past also. And so this is showing you the temperature and carbon dioxide record going back 800,000 years. So the red is temperature, the blue is carbon dioxide. And the first thing you'll notice is they track each other beautifully because they have to. That's the way the greenhouse effect works. More carbon dioxide, higher temperatures, less carbon dioxide, lower temperatures. You'll also notice that we should have some concern based on this because, remember I told you we've got a 50% increase in the carbon dioxide concentration since the pre-industrial times. And look at what 50% increases in carbon dioxide have done in the past. They've taken us a range of 10 degrees Celsius, 18 degrees Fahrenheit, which is from deep ice ages into warm interglacial periods like we're in now. So if you go by this data, you should be very, very concerned about what a 50% increase in the carbon dioxide concentration is going to mean. And of course, models confirm that we should be concerned about this. And so you've got the basic idea now of the 1, 2, 3 science, and this is the point where I like to challenge the audience here. This is so simple that you might wonder, how is it possible for so many politicians to have difficulty understanding it? And so your challenge question is, who was the first major global leader to speak out on a global stage and say, look, this is simple science and it's a major problem? So Al Gore is the most common answer that people give. And in fact, I do believe that Al Gore probably was aware of it before anyone else who we would consider a major global leader. The problem is that back in 1989, you all in Tennessee knew who he was because he was your senator. But the rest of the world had not heard of him yet. But there was a different politician in 1989 who gave a speech to the United Nations on this topic. And this is what she said. What we are now doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways. This is Margaret Thatcher in 1989. So if anybody ever tries to tell you that this is some sort of liberal, democratic idea, the first major global leader to speak out on it was one of the founders of modern conservatism. And it's worth watching her entire speech where she talked about this and the importance of taking immediate action on it, which didn't happen. But so we should have been listening to the conservative politicians at the time. And just in case you run into anybody who says, yeah, but that was the Margaret Thatcher type of conservative, what does the Donald Trump type of conservative say? From Donald Trump in 2009, if we fail to act now, it is scientifically irrefutable that there will be catastrophic and irreversible consequences for humanity and our planet. Admittedly, he said something different a few years later, but you can see there should not be any political dispute about this topic. It's a scientific topic. All right, we've gone through the basic science. Now we're going to turn to the consequences. I'm going to go very fast through the consequences because I think a lot of them are familiar to all of you. There are many, many consequences of global warming. To make it simple, I like to group them into 5 basic categories. So the first category is that regional climate change. It's the idea that even though the Earth is warming on average, you don't get the average everywhere. And so here is a map of the Earth showing you red is warmer than the average for a region, blue is colder than the average for regions. This is from NASA. And I'm going to start the video, I hope. There you go. And so you can see the years going by there. And you can see, the regions, it looks kind of random, right? As we're in the early part of the 20th century, some places get warmer, then they get cooler, then they get warmer, then they get cooler. It just looks kind of random. But then we get into like the 1980s and 90s. And it doesn't look so random anymore, does it? That is what's happening to our planet. And you notice the deepest red regions, most of them are up here in the Arctic, so the Arctic is warming much more and much faster than other parts of the world with all kinds of consequences. And there's lots of other consequences that come about because of this regional climate change. I'm just going to go through a couple of them for you. This one is one that you'll almost certainly have noticed. And this is a graph from James Hansen, famous climate scientist now at Columbia. And what it's showing you, if you know statistics, what he did was and if you don't know statistics, just ignore the details here and I'll come back to it. If you know statistics, what he did was he took all land temperatures over the northern hemisphere for the 3 months of summer and put them all on the same normal distribution, bell curve. And so basically what it's showing is the frequency of summer, I don't know, summer's not showing up there, frequency of summer days. So the normal summer day is some certain temperature, and most of them are normal, and some are hotter than normal, some are really hot, some are cooler than normal, some are extremely cold. And this is for the period 1951 to 1980 that he made this graph. Then he did the graph again for more recent period. He's done this lots of times. I happen to have on my show here the 2005 to 15 curve, and it's shifted even more since then. And what you'll notice is that the entire curve has shifted to the right, actually by a full standard deviation, so that today's normal, right, the peak of the curve, is what we were calling hot a few decades ago. And you notice this, right? In the summer, there's more really hot days than there used to be. And this is why. And lots of other consequences of that. But then the next one is we get an increase in storms and extreme weather. Why do we get an increase in storms and extreme weather? Because remember what the greenhouse effect is. It's trapping energy down near the surface and in the lower atmosphere and the oceans. And think about what weather is. Weather is energy from the lower atmosphere and the oceans. So more energy down there, you're going to get more extreme weather. It's pretty obvious that that must be a consequence you should expect. And of course, the data show that we are getting more of these weather extremes. Incidentally, you might wonder how much more energy is being trapped down in Earth's system. And it turns out there's actually two different ways to measure how much extra energy is being trapped. One is by looking at how much the oceans are heating up, and the other is actually by direct satellite measurements. You can measure the incoming sunlight and the outgoing infrared light. If there was no global warming occurring, those two things would be in balance. But there's actually less infrared light going out than the sunlight coming in. That's Earth's energy imbalance. And it turns out the amount of that energy imbalance is about 1 watt per square meter. If you know anything about solar energy, you know the solar constant is about 1,300 watts per square meter, the amount of sunlight coming in. But 1 watt per square meter less than that is coming out. If you multiply that by the surface area of the Earth, you find that's 500 trillion joules of energy being added to Earth's system, climate system, every single second, which is the equivalent of detonating 8 Hiroshima-sized nuclear bombs every single second, or having 1 million lightning bolts per second, or 4 ongoing hurricanes at all times, or 6,000 Category F5 tornadoes per day. That's an incredible amount of energy that's being trapped. Extra energy down here on Earth. You might wonder, with so much energy being trapped, why aren't we seeing even more extreme effects? And the answer is because most of it's just going into the actual heating of the average temperature and of the average ocean temperature. But if anybody's wondering, why do we see more extreme events? That's why. The third major consequence of global warming is the melting of sea ice. So here we're talking about ice up in the Arctic Ocean. We know that's the part that we saw as warming the most, so not surprising that the sea ice is melting. And you can see there the general trend downward of the amount of summer sea ice, comparisons of a few select years there, but very clear we're losing sea ice in the Arctic. Why should we be concerned about that? It doesn't affect sea level. That's why I've separated the sea ice from what we'll talk about with sea level next. It doesn't affect sea level because this ice was already floating, so when it melts, no change in sea level. However, remember those things about reflectivity that we talked about, like between Venus and Earth? Ice is very reflective. Water, liquid water, is much more absorbing. So as we lose ice coverage, Earth is actually absorbing more sunlight, and that's going to amplify all the other effects of global warming that we're getting just from our greenhouse emissions. So this is a very, very concerning effect because of its possibilities for amplifying everything else. There's a number of other things. It may be tied to some of these changes in the jet stream and what you hear about in the news of the polar vortex that's led to some of the really weird weather we've had in recent winters in particular, and so on. The fourth major consequence is that rising of sea level. Now, the rising of sea level is actually happening for two reasons. The first reason is that as the oceans warm, they actually expand a little bit. If you measure put a cup of water down and raise its temperature and try to measure its expansion, you'll never be able to do it in a cup on a table. But with the miles deep of ocean water, that expansion, thermal expansion of water is noticeable, and it's been responsible for about, somewhere between about 4 and 8 inches of sea level rise already over the past century, just the thermal expansion of seawater. In addition, you've got the fact that glacial ice that's on land, mostly in Antarctica and Greenland, as that melts, that water flows into the oceans, and that raises sea level. And that has the potential to be the much bigger contributor to sea level rise. And even though the sea level rise to date is relatively small, about 8 inches, that tends to be amplified by a storm surge. So the storm surge doesn't go up by 8 inches, it goes up by several times 8 inches. And that's why we see this much greater damage along coastlines for more recent storms. And if sea level rises, the red here shows you if it rises by a meter, regions of the southeastern United States that will be flooded. And that meter of sea level rise, about 3 feet, is kind of in the mid-range of what we will expect by the year 2100, when today's kids will still be alive, if things keep going the way they're going. And just to get the sense of it, I don't want to be alarmist, so don't worry. This is not going to happen for thousands of years. But if we keep going the way we're going, we will eventually melt the ice caps completely. And you might wonder, what happens to sea level then? And the answer is, it will rise more than about 70 meters, 240 feet. So even though, from a human standpoint, if this is going to take thousands of years to happen, people could migrate inland by that time, so it's okay. But we have this really interesting vision of our descendants a couple thousand years from now needing deep sea diving equipment to visit the ruins of today's coastal cities. And then the fifth major consequence of global warming is what we call ocean acidification. You hear less about this one in the news than any of the others, but it's actually at least as important as all the rest. And what this is it turns out we're dumping all that carbon dioxide into the atmosphere that's raising the concentration, but it turns out only about half of what we're dumping into the atmosphere is staying in the atmosphere. Most of that other half is being absorbed, a lot of it in the oceans and the rest by the land. And in the oceans, that dissolved carbon dioxide reacts and becomes carbonic acid and makes the ocean water more acidic, which has all kinds of effects on corals, on fisheries, and the reason this could be as significant as all the others from a human standpoint is because so many people around the world depend on the ocean for their food supply, and this could easily cause great damage to that. So those are the 5 major consequences of global warming, and then on top of that, you have to worry about what we might call possible tipping points, places where these things interact with each other, and something then really shifts in the climate system to a point where maybe it becomes almost irreversible. Because those other 5 we've talked about so far, they're all mostly reversible in principle. But if we hit a tipping point, then maybe not so much. And so that brings us back to, if I stop the talk right now, I would send you all home, and you would probably think our future is a choice between bleak and bleaker, like the media talks about all the time. But remember, that's not the only possibility. There's other possibilities because we know how to solve this problem. How do we know how to solve this problem? Because we know what's causing it. The burning of fossil fuels, primarily. So therefore, we know how to solve it. Stop. See, easy, we're done. Okay. Well, of course, it's not quite that easy because we like the energy that we get from fossil fuels. So now we want to talk about solutions. If we're going to have solutions, we need to find a way to be able to keep our lives going and our economy going, even while we somehow get away from what's causing this problem. And so that brings me to our solutions page, and I always love to put up Greta here, because her quote at age 16 really encapsulates everything we need to know about this. I want you to panic. I want you to feel the fear I feel every day. And then I want you to act. So what she's saying is, yes, you should be really scared of this like she is. But don't just be scared, do something. And so what can we do? Well, amazingly, we could, right now, stop using fossil fuels and have no change in our lifestyles. In fact, they actually get better. That's because we have existing technology that could replace the energy that we get from them without any downsides. And there's basically three categories of technology that can do that. The first is energy efficiency, where you get the same benefit for less energy and less cost. You don't maybe think of energy efficiency as an energy source, but it really is, because if you need less energy to do the same thing, it's just like you found more energy, right? Because now you've got more energy from everything else to do it. The second category is renewable energy that does not emit any greenhouse gases. And just to give you a sense of the possibility, the total amount of solar power reaching the Earth is about 20,000 times what our civilization, the whole world together, uses. So if we could tap just 1/20,000th of all that incoming solar power somehow, that could replace all the energy that we get from every other source right now. And the third category of solution that we have is nuclear power. And I know a lot of people have a lot of different reactions when I say nuclear power, but nuclear power does not produce any greenhouse gases. And we already know how to do it. France gets 70% of their electricity from nuclear power. So nuclear power is, again, one of the potential solutions. So between these three technologies, we could right now, in principle, get all the energy we have today, but without any more greenhouse gas emissions. Incidentally, when I say right now, obviously, it's not like flip a switch, right? So you might wonder, how long would it take us to do this? And so I gave this talk at a retirement home, and somebody in the audience asked me, how long would it take us to make this transition? And I said, well, I don't know, what do you think? And a guy in the front row, 96 years old, raised his hand. He says, I know the answer. He said, 3 to 5 years. I said, wow, I never heard anybody say it could be done that quick. He said, that's because you didn't live through World War II like I did. When we transformed the entire economy and manufacturing base of this country in less time than that, because we had to win that war. So if we cared enough and we felt it was important enough, we could do it now with this. And that's just the technologies we have today. If we can find a way to do that today and stop emitting greenhouse gases today, that gives us some time to come up with other energy solutions. For example, advanced carbon neutral biofuels, like biofuels from algae that can actually be used to power today's jet engines. You don't even have to replace the jets. You just have to replace their fuel with this other fuel that absorbs more carbon dioxide when it grows than it releases when it's burned. Solar energy from space, it's one of my favorites. One of the difficulties with solar energy is that it only works when the sun is shining, it's not cloudy, and it's not daytime. But in space, if you go up to a high orbit, it's never cloudy and it's never night. And so you just put your panels up in space and beam the energy down to Earth. There's actually several recent ongoing efforts to develop solar power from space. And my personal favorite, nuclear fusion. So for nuclear fusion, somebody in the audience would have to let me borrow your kitchen sink. And imagine that I borrowed your kitchen sink, and if you remember the Back to the Future movies, I have Mr. Fusion. And so I hook up Mr. Fusion to your kitchen sink. I turn on the water, and I apologize for your water bills because I'm not going to turn it off. And I let the water flow through your faucet, and I extract all the hydrogen from it and put it into Mr. Fusion and generate energy from it. Mr. Fusion attached to your kitchen sink could power the entire United States. We wouldn't need any other energy at all. Just your kitchen faucet. That is what fusion potentially has available to us. If we could do that, it would be incredible. Of course, we haven't gotten there yet, but we're working on it. And one of the things, remember I told you we want to go to a post-global warming future, and I said so far we could stop emitting greenhouse gases, but we still got the problems we've already created. So if you want to go to a post-global warming future, you have to undo the damage that we've already done, which means you need to remove carbon dioxide that we've already dumped in the atmosphere from the atmosphere. People are already developing technologies to do this, but there's a problem with it. The big problem with active carbon dioxide removal, there's also passive removal technologies, but they probably can't get us far enough to have a true post-global warming future. But we're going to need active ones. And the problem with active carbon dioxide removal is that it's energy intensive. We would probably need something like 50% of the world's current energy use to begin to make a real dent in the carbon dioxide concentration on Earth, even if we scale up this technology that's being developed now. Where are you going to get so much energy from? How about fusion? If we develop fusion, then we don't have energy problems anymore, right? We'll have plenty of energy available to pull all of that carbon dioxide out of the atmosphere. I'm going to come back to that, but I want to take one brief aside to say, what can we do specifically to help us get on this path? And I won't spend too much time on it, but I would say, in my personal view, and I'm admittedly going from scientific stuff into personal opinion at this point of the talk. In my personal view, the reason we have this big problem today is because fossil fuels are artificially cheap, because we've been subsidizing them by enormous amounts. For example, the health costs of air and water pollution are not built into their price. These are what economists call externalities. The cost of protecting the global oil supply is not built into the cost. The direct subsidies and tax write-offs are not built into the cost. And maybe even the most significant, if you look back at all the terrorism and authoritarianism that we're seeing in the world today, almost all of it is paid for with money that we gave them by buying their fossil fuels. Russia, I would argue, would not have been able to invade Ukraine without the fact that we've been buying all these fossil fuels from it for such a long time. And then there's the environmental damage and so on. And in fact, the IMF recently estimated that total annual subsidies for fossil fuels are $6 trillion per year, $1 trillion per year alone in the United States. If that was part of the cost of fossil fuels, we would have stopped using them decades ago, because they're actually more expensive than those other alternatives that we talked about. And very briefly, there's basically two ways of addressing those externalities. One is you can have government subsidies to counter the other subsidies, right? And that's kind of what the Inflation Reduction Act did, right? Gives all these tax breaks and things like that. The other is you could put on a carbon tax. and use that to recover those externalities that the economists are talking about. And personally, I like that second idea. If it were up to me, I'd go with the carbon tax. And if you happen to agree with me and are wondering what you can do about that, join a group like the Citizens Climate Lobby, or if you're a college student, join Students for Carbon Dividends. These are groups that are pushing for a carbon tax and dividend plan. And you can read about the details of how those plans work, but they're very, very well developed in order to make it so that you recover those externalities, make a more fair marketplace, actually becomes a freer market than what we have today, and does so in a way that doesn't have unnecessarily hard impacts on lower income people through this dividend program. And so that brings us back to the future. Whatever you think about the particular thing we should do to help us get those solutions, the basic way to get to a post-global warming future is actually pretty simple. It just takes two simple steps. Number one, stop making the problem worse. We need to go to zero carbon emissions as fast as possible. And then by doing that, we avoid the risk of hitting a tipping point. And even though we'll still have the consequences to deal with for now, that buys us time to develop fusion or solar energy from space or these other things, and then we'll develop those new energy technologies, start the active carbon dioxide removal, and start to bring the carbon dioxide concentration back down. And you can easily imagine, let's say we reach zero carbon dioxide emissions by 2050, and by that time, we've also developed, let's say, fusion. And so we start active carbon dioxide removal, and we bring down the concentration by a couple of parts per million a year. By the time you get to 2070, 2080, we've actually brought the carbon dioxide concentration back down to a level where the climate is essentially being restored to what it was before we started messing with it. And not only have we restored the climate, so we're in a post-global warming future. Remember, the way we did that is because we have so much energy available now. So we have to figure out what to do with all that extra energy. And that brings us to our final idea here, a tale of two futures on one planet. On the one side, we can just keep doing what we're doing, the status quo. And that represents what I think of as an existential threat, a true threat to the existence of our modern civilization. It's, again, don't want to exaggerate, it's not a threat to life on Earth. Life on Earth is going to be fine with or without us. Well, a lot of species will go along with us, but life as a whole will be fine. Just like it was after the dinosaurs got killed off, right? We're probably not going to be able to kill ourselves off completely. There'll still be humans around. But the civilization that we enjoy with PowerPoint and glides and all that, we won't be able to keep that if we keep going the way we're going. But the alternative is not the bleak and the bleaker. The alternative is we do what we're talking about, and we get a post-global warming world, and now think about what we're going to do with all that extra energy. Well, with all that extra energy, it would be, in principle, fairly easy to eliminate global poverty. Fresh water is a problem that you hear about a lot. It's not a problem if you have plenty of energy, you just desalinate seawater. Oh, well, you're worried about all the mining that we're going to have to do to get our, renewables and things in the meantime, and we're still going to need other mining, and that does a lot of damage to the Earth. So we just say no more mining anywhere on Earth. Go get it from the moon and asteroids, which if you got plenty of energy, no problem. So we just declare Earth basically a national park. And so much more. So this post-global warming future is truly this amazing future that we could have by the time today's college-age and younger people reach their 100th birthday. And so I have two final exercises for you. One for the young people, one for the old people. Or older. Imagine it's your 100th birthday if you're one of these people who's still going to be alive in the year 2100 and beyond. Do this exercise. Write your story. How did we achieve a post-global warming world, and what role did you play? And I think if you do that, I encourage you to actually do this. It'll help you think about what you want to do with your life as you move forward. And for those of us who are older and aren't going to be around to see the year 2100, we can think of things a slightly different way. I want you to imagine writing a letter to your grandchildren that you're going to put in a time capsule for 50 years. Why did I choose 50 years? Because in 50 years, on average, with 25 years between generations, on average, at 50 years, your grandchildren will be exactly the age you are now. So imagine them sitting in an audience 50 years from now, and they go and they find your letter that you wrote, and they open it. It says, "Dear grandchildren, as I write this in 2023, many people are arguing about whether global warming is a real problem. If so, how serious it will be for you when you are my age. I have examined the evidence, and I have decided to." You write in what you're going to do. "I hope your world is a good one. Love, you." And ask yourself, when they open this letter 50 years from now, what will they say about whatever you wrote here about your decision? And so that's it. I have a couple resources that if you want to learn more about this, the Global Warming Primer book that's posted on the website there. I have a book on this topic for kids also called The Wizard Who Saved the World, and you can see it there being read from the International Space Station, and you can watch the video of the reading at storytimefromspace.com. And I also have a middle school unit on climate change as part of an entire Earth and Space science curriculum that I have posted free on the web at grade8science.com. So if you know any middle school teachers, they can use that in place of whatever other curriculum they're using for their Earth and Space science right now, and it's all free. Before we move on to questions, just very important that you all pay attention to what's coming up here, right? You've got the annular eclipse in October, not so close to here, around here, partial eclipse, but where you are, this total path next April 8th is going very, very close to you. You can download my free app, and you'll see that here in Memphis, you've got about 98% totality. You might be tempted to think that 98% is almost 100%. And mathematically, it is, but in terms of solar eclipses, it's the difference between day and night. Even at 99.9%, the sky is still very bright compared to at 100%. And only at 100% can you take off your eclipse glasses, see the corona, see stars and planets. So my goal is to inspire all of you, to inspire everyone else in Memphis to move the entire city, every single person, onto the path of totality next April. Right there you see how close you are to the path. So you can use the app to figure out exactly where you want to go. And those are all the rest of my books and stuff, and I'll stop there. Thank you very much.